Welcome to my talk. My name is Muhammad Ibrahim. Actually, the common problem to control the autonomous vehicle is the uncertainty due to external disturbance. For this reason, we proposed Linux-supported approximated optimal control approach for autonomous vehicle. Actually, the autonomous vehicle, for example, unmanned aerial vehicle, are used for many important applications. For example, search and rescue missions. For these missions, we need to minimize the energy consumption due to battery limitations. Also, we need to take into account the vehicle dynamics and constraint. So we proposed optimum control. However, in these applications, there are many challenges. For example, as I mentioned at the beginning of my talk, the common problem is the disturbance, for example, wind disturbance. While ignoring this disturbance might lead to instability of the control system. In addition to low computational power demand of the autonomous vehicle. To consider all these aspects, we propose Linux-supported approximate optimal control approach. In my talk, I will explain how these aspects are considered. In this work, we assume state-dependent disturbance based on a realistic scenario. For example, when the autonomous vehicle is moving with low velocity, so the wind effect is less than in case of moving with fast velocity. So here, the disturbance depends on the vehicle velocity. To achieve all these aspects that I mentioned before, we propose Linux-supported approximated optimal control approach. The main idea here is to drive an explicit solution of the optimal control problem using series expansion approximation based on Albrecht method. Consider nonlinear vehicle dynamics. This explicit solution, which is just state feedback control law, is applicable for real-time implementations. And this control law can be validated. And also to decrease the impact of the disturbance, the controller are defined as a function of disturbance parameters, which are learned online. So how this explicit solution of the optimal control problem can be calculated? Actually, solving the optimal control problem is computationally expensive and is challenging to be implemented on the autonomous vehicle. So we propose to calculate an explicit solution of the optimal control problem. Both the cost function and the vehicle dynamics are approximated using power series expansion based on Albrecht method, take into account some conditions and assumptions. Actually, the solution accuracy depends on the approximation degree of the power series expansion. So, how this explicit solution is calculated? First, both expansions are obtained using Albrecht method by solving for each degree the Hamiltonian-Jacobi-Bellman equation, equation number 1, and the first derivative of this equation with respect to the control law, equation number 2, and assuming the control law and the optimal cost function are defined as a power series. In the next step, one collects all terms of the second degree of the first equation and first degree of the second equation, leading to solve an LQR problem. Then, the higher degrees are solved iteratively in the same manner until the desired degree of the approximation has been reached. At the end, all terms are linear with respect to the state and unknown parameters. So how this controller updates the unknown parameters online? So we propose to use machine learning scheme to determine the unknown parameters, to update the controller parameters, to reject the disturbance and improve the controller performance. In this work, We propose state-dependent uncertainty, which is learned online using the measurement collected during the mission. This data includes state measurements and the control inputs at the previous time steps, and the difference between the predicted and the estimated error. In principle, we can use any learning approach to learn these disturbance parameters. To validate the robustness of the proposed control law, to learn and reduce the effect of the external disturbance, we consider quadcopter, covering a known environment with different disturbance scenario. In this work, the quadcopter is defined by 12 states and control using 4 rotors. And the quadcopter dynamics are defined by nonlinear model, include navigation equation, kinematic equation, force equation, and the moment equations. Considering these nonlinear dynamics in optimization-based control is completely challenging. So, in order to make the approach computationally efficient for embedded implementation, we propose to use multivariate learning regression for learning online the disturbance parameters. We propose to use also gradient descent scale to determine the unknown parameters of the learning model. So the objective here is to minimize the difference between the actual error and the estimated error. Then the parameters of the learning model are updating by this updating law. So these parameters are used to tune the controller to reject the disturbance and improve the controller performance in order to track the reference more accurate. Now we need to validate the proposed control law. First, we compare between the first order approximation and second order approximation of the explicit solution of the optimum control problem. What's the difference? The first order doesn't consider the disturbance parameters, while the second order considers the disturbance parameters as a tuning parameters. As we can see, the second order can alleviate the effect of wind disturbance, while the first order is more sensitive to wind disturbance, which might lead to collide with obstacle. So learning the disturbance parameters lead to safe flight and more accurate performance. Actually, considering the nonlinear vehicle dynamics in the optimization-based controller, it's completely challenging to be implemented on embedded system. So we need to test the real-time visibility of the proposed control. As we can see, considering the linear dynamics of the autonomous vehicle, and also considering the disturbance parameter of higher order approximation, doesn't affect the computation time, which is around 11 microseconds. For more validation of the robustness of the proposed control law, we proposed 100 simulation with random wind disturbance. As we can see, the region of actual path is reduced using second order approximation, which addresses the wind effect as a tuning parameters. While the first order is more sensitive to wind disturbance, which might lead to collide with obstacles. As we can see also, the average value of the root mean square error between reference and the actual path, it's about 2 meters using second order approximation, which improves the control performance more than 10 times compared to the case of the first order approximation, which is around 25 meters. So safe flight is ensured for all uncertainty scenarios without obstacle collision. So now we need to validate this control law for long time mission. We also validate the proposed control approach on long mission as area cover on Calaton environment with different wind disturbance cases. In this work, we propose to implement moving horizon planning approach using mixed integral linear program to handle the environment dynamics to achieve the mission objective, for example, area cover, with minimum energy consumption. Take into account the vehicle dynamics and the constraint that represent the capability of the autonomous vehicle to guarantee that the reference planner generate visible path. In this scenario, the quadcopter is occupied with a sensor to cover a mission space while avoiding obstacles despite the wind disturbance. So far, now to summarize the proposed control approach. Controlling autonomous vehicle needs to achieve limited computational time demands and also needs to consider nonlinear continuous time dynamics of the autonomous vehicle. Actually, it is difficult to be implemented and solved in real time. So we propose to use approximated explicit control loop using Albert method. And we propose to use learning scheme to learn the disturbance parameters to handle the disturbance and to compensate the approximation errors in order to improve the controller performance. Actually, this controller approach can be implemented efficiently in real-time implementation. Also, this explicit control loop can be validated using sum of square method or set-based approaches. We proposed also to use moving horizon planning approach using mixed integral linear programming to cover an area with minimum energy consumption while avoiding obstacles, considering vehicle dynamics and constraint. The future work will be regional stability verification of the proposed control loop. We can consider a bidirectional interaction of the planner and the control. So the high-level planner can consider the capability of low-level controller as a state-dependent uncertainty. The future work will be experimental validation of the proposed control approach. We can consider also cooperative area cover using multi-vehicles. Thank you for your attention, and I hope you enjoyed the video.